Alright, what's up everyone? This is Codeforces Latoken, round 1. It's a combined round, which means it's rated for me. So I probably won't be having too much commentary, but aside from that, if you're competing, good luck. Also, I have my hair tied back today. Let's see whether that helps or not. Alright, so I said I'm going to start with problem B because of a weird scoring distribution. I might as well just load up A through D and see what they are. See what's the interactive problem. D is the interactive problem. Okay. Let's see. Little Dormy received histogram with n bars of height this. More really imperfections. To modify the histogram, he can decrease any number by 1. He defines the ugliness of his histogram as the sum of the vertical length of his outline and the number of operations he performed on it. The red line's the vertical. Okay. So we only want to decrease. The only time a move is optimal is if in one move we can remove 2 lines. Because if it's like in this contiguous chunk like this, then removing that would not give anything. Removing that would give 2 in 2 moves. So I might as well just not remove it at all. The minimal ugliness you can achieve. Yeah, so we just care about peaks, I guess. We want to make everything equal to its peak. Let's try this. I just want to eliminate like peaks like that, yeah. Long res is equal to 0L. What is a total height? Okay, I guess the total height is like this. So if how do we find this height? I guess we just add all the lines to the left of it. So assume you don't make any moves, then we do something like this. So we have this height and then this height. I guess it's just like the absolute value. Yeah, because like the height of this and this increases this much. If it's like 0, then increases by 1. And then this over here is increased by however much is over here. And then this increases by the height of the last thing. Okay, so remove. And so if array at 0, do we have at least 2 elements? No, we sometimes only have 1. Okay, so if n is equal to 1, then with the cost of 1 operation we can remove 2. Because normally it would be like both sides. So it's like height 4, height 8, but we can have in height 4. I guess if it's like it used to be 10, it's just 5. It's just can we make it equal to 0? Yes, we can. Okay. So it's just this. And then this is a case in which we remove over here, where if array at 0 is strictly greater than array at 1, then obviously we want to, the amount we can decrease it by, if it's like height 1, we use cost 1 to get rid of 2, so it's essentially just this, and then array 0 becomes array at 1. Yeah, it's like, it's just decreasing this. And then now it's like, we're potentially going to need to decrease this. I mean, if it's smaller and this is bigger. Yeah, because this histogram, I guess if it's something like a big bar and then something like this, something like that. Int level is equal to if this is strictly greater than level, then one thing we want to do is we want to take this height, decrease it up to there, array at I minus level, and then this becomes level. If array at minus 2 is strictly less than array at minus 1, then res, it's this height difference. And then just for consistency, I'll do this, although it's not necessary. Okay. 17 and 12. Am I using longs? I am. Okay, we got B. I think we go into C for now. I want to at least read it. When he's not training for IOI, little Awan enjoys playing with puzzles of various types to simulate his brain. Today he's playing with a puzzle that consists of a 2x(n) grid, like this. N small, okay, it's not that big. Goal of little Awan's puzzle is to make no numbers on the same column or row. Wait, it's to make sure no numbers on the same column or row are the same. Okay. To achieve this, he is able to swap the numbers in any column. However, after solving the puzzle many times, he got bored and began wondering about the number of possible solved configurations. To achieve this, he wants to swap the numbers in any column. Okay. So it's 2 to the power of n, like total possibilities, I guess. Okay, this shouldn't be too hard. We can just like, it's like creating a graph of some sort, I guess. You could think of it like that. I solved a similar problem like this in the past. So pretty much what we do, okay, so it is a permutation. And numbers in each column and row will be pairwise distinct. Static final long mod. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, wait, can we swap the numbers in the columns, right? I want to make sure no numbers on the same column or the same row are the same. swap the numbers in any column. Yeah, okay. So we need to check if there's if array of I is equal to, this is set to true. If it's like this, then it's impossible to have the columns to match. So now we just make sure the rows match. And the way the rows match, it's just like union find. Just like component, like finding number of components, I guess. Alright, because if 2 and 3, 3 and 2 has to be flipped, 6 and 8, 8 and 6 have to be flipped, 5, 7, 1, 4, 7. Oh, actually, that's true. We have to think about cycles. Because if it's, I guess if it's like 5, 7, 7, 4, we want to do a 2 coloring. I want to count how many components. So this is how many components there are, so Boolean. Okay, so how do I do this? 2, 3, 3, 2. So it goes 5, 7, 7, 4. Because we can think of these as edges. Yeah. Because if we have something like I guess so edges at okay, and color, well, I guess, yeah. So if we haven't seen this component before, then we want to DFS on it. Color v is equal to 0. Components increase by 1. And then so look at anything that's adjacent to it. So if we haven't seen this node before, then we want to visit it. Color at next is equal to color at per number 1. Then we add it into our BFS. Otherwise, if these conflict, then conflict is equal to true. Yeah. Because if we have two adjacent nodes that are the same color, then we can never make this good. So if we conflict, otherwise we do this. So while okay, so it should be 2 and 0. Two and 8, hold on. That's not right. Because we haven't added from 5 to 7, 7 to 4, 4 to 1, 1 to 5. This is an odd cycle, right? 5 goes to 7, which then goes to 4, 4 goes to 1, and then 1 goes to 5. Oh wait, hold on. 5, 7, 7, 4, 4, 1, 1, 5. 8, 6, 6, 8. Oh wait, it is 2 and 8. I read it as 2 and 0. Holy shit. Okay. Yeah, my eyes don't work. Oh wow, wrong answer. Interesting. Okay, well, let me make sure this isn't... Okay, so it is pretty easy. I'm gonna try to debug this for a little bit of time. If these are equal, then there's no ways to do it. That's completely good. If we have 0 components, right? Because if there's a self loop, then no matter how we color it, it can never work. The number of components increased by 1. If conflict, then we do something like this. Yeah, because if we flip 1, then that's determined by that. Should I just do... I think I'll just do A really quickly. Today you're playing a red and white coloring game. You're given n by n of 3 different characters. Recolor the blank cell to red or white such that every red cell only has white neighbors and no red ones. Wait, you're allowed to... You need to recolor the blank cells red or white so that every red cell only has white neighbors and no red ones. And every white cell only has red neighbors and no white ones. Oh, so this is checkerboard. Oh, okay. Yeah, I'll do this really quickly. They basically gave a solution in samples as well. How do I do this? How do I do this? If this is equal to 0, then we use an R. No, use W, otherwise use R. This 1. Public static Boolean check. Okay, so res has none of this, so So, okay, if this does not equal to this, and grid at RC does not equal to res at RC, okay, and then otherwise we do continue. What is this reload class thing? Oh, this is supposed to be res. Like, what on earth does that mean? No. Yes, no, yes. Okay, we'll just submit this right now. Does it work? It probably does. It's not that hard to show why. Let me do this. Okay, we got A. We need to figure out what our bug in C is. So if everything is the same, or like if there's some pair such that no matter how you flip it, it's going to be the same. Otherwise, if it's like 5 to 7. Yeah, because if it's something like 1 to 2, 2 to 3, or I guess 1 to 2, 2 to 1 would be okay. 3 to 1. Oh, I guess we don't actually need to do this. Okay, so if 420 is equal to 69. Yeah, I think I was just being dumb. Like, that coloring thing doesn't actually matter at all. What is going on? Do not show dialogue in the future. Pretest. I'm gonna restart. Actually, wait, hold on. Is that why, maybe? That might be why. On pretest 1, pretest 2, pretest 3, pretest 5, pretest 7, pretest 8, pretest 10. Okay, we got C. It was just a very silly mistake. Okay, so problem D and then E. I guess F1. I'll open up E and F1 just so I don't have to wait for it to load. There's 2 interactive problems. Wait, are you serious? What on earth? That's what? That's strange. What? Okay. Little Dormy was faced with an awkward problem at the carnival. He has to guess the edges of an unweighted tree of n nodes. The number of a tree is 1 to n. It's almost 2,000. The game master only allows him to ask one type of question. We pick a node R, and the game master will reply with an array of this. Make at most this. So you pick a node, and then the game master will reply with this array, where d at I is the length of the shortest path from node R to I for all I. That's like this. Okay. So we have to figure out the structure of the tree. Place the node R, and the game master will apply with an array like this, where di is the length of the shortest. Oh, okay. One interesting thing is that I wonder if we can do that. where it's like, is it the ceiling of n over 2? It is. What if we like do a 2 coloring of a tree and we only check nodes of 1 color? Is that enough to get information for everything else? Because, okay, let's say we like query a random node. Say like, for example, is 1. Then we know that everything of even distance is the same color, everything of odd distance is another color. Let me write this down. So think about 2 coloring of tree. And this is by part type because it's a tree. So if we can figure out all edges, an edge from A to B exists if and only if the distance from A to B is equal to 1. Yeah, so I think this means we can just query whichever is a smaller color, right? I'm gonna try that. Let me think about it. Because every edge has exactly one every edge consists of 1 black and 1 white node. So if everything is a 1 black node and 1 white node and an edge connects that, we only use just over half of the queries. Yeah, I think this works. Okay, let's try it. So we have n over here. We'll begin interaction. Answering is not considered a query. So how do we ask? Okay, question mark and then this. N is at least 1, so no, I guess we do need to read an array. So we do this into initial read array n and file st. Okay, well, if n is odd, then the largest of the minimum black and white is a floor of n over 2. So we can guarantee we have enough queries. If it's even and the number of black and white is the same in everything, then how do we do that? I mean, then I guess it doesn't matter, right? Yeah, we just need to get like a list of candidates. And odd count is equal to 0. Okay, so if the initial distance, if this is equal to 1, then we know that there's an edge from 1 to here. Initial of v mod 2. Okay, if odd count is equal to even count. No, if odd count is equal to, if odd count plus odd count So this is I think this is a special case. Yeah. If odd count is equal to even count, then that means we just need to get like a list of nodes to search from. Sources. Okay, so if odd count is equal to even count, then we want to query the same nodes. We want to query even because we already queried a black node. We might as well just query the rest of the black nodes. If initial v mod 2 is equal to 0 and v does not equal to 1, or hold on, we can just do this. V plus 1. Okay, so otherwise odd count and even count is uneven. So even if we made a query in this wrong section, we'll always have enough. So if even count is less than odd count, else, then odd count is less than. Okay. So we first query this is equal to, we do this. So if this set v, okay, so if a distance at v is equal to 1 and v is strictly greater than the root, and it's like root. Okay, so we do this, and then on another line we just do that. Okay. I want to test this tree, the second sample. 1, 3, 2, 4, 3, 5, 4, 5. Okay. Okay, so size is 5. If we ask for 1, then distance from 1 to 1 is 0. Distance from 1 to 2 is 1, 2, 3, 4. Distance from 1 to 3 is 1. Distance from 1 to 4 is 1, 2, 3. Distance from 1 to 5 is 2. Then we ask 3. Distance from 3 to 1 is 1. Distance from 3 to itself. No, distance from 2 to 3 is 1, 2, 3, 0, 1, 2, and then 1. Well, yeah, because 1, we asked it on a larger number. Yeah, but the max, yeah, this is fine. 4, we get 1, 2, 3. 3, 1, 2, 0, 1. That's not right. 1, 3, 3, 5. What on earth happened over here? There should have been an edge from... How did that even happen? Wait a minute. One to 3, 3 to 5. Did it just like ignore queries of 4? Or what? I thought of a better way to do this. What if we just do this? Static file long. To do this, pair 1 and b plus 1. Public static long pair. Do this. Okay. Edges.add pair. Pair the root in v plus 1. I guess if we do this, four long x's edges. Okay. 5. If we print 1, 0 from 1 to 2 is 1, 2, 3, 4. Print 3 is 1. Print 4 is 1, 2, 3. Okay, we print 3, where we go 1, 1, 2, 3, which is 2. No. 1, 2, 3, yeah. This is 0, 1, 2 is 4, 3 to 5 is 1. And we query 4, where we go 1, 2, 3, 1, 1, 2, 0, obviously, and 1. Okay, that makes a little more sense. I'll submit that right now. Let me see. 2, 4, 1, 3, 3, 5, 4, 5. Yeah, that was pretty easy, I think. Yeah, there's already 200 solves on it. How many I think? There's almost that many queries. It'll probably be okay. Yeah, E. Okay, so E is the next easiest, I guess. Pretest 4, pretest 5, pretest 6, pretest 8, pretest 9, pretest 12, pretest 14, pretest 18. Okay, we got it. 483. That's pretty fast, honestly. Yeah, I think that's fast. Problem E. This is an interactive problem. Again, interactive problems. Woo. Hopefully there aren't that many queries. Okay, number was 500, so it's probably fine. The XOR sum of an array is defined as a XOR. Okay, yeah. Little Dormy received an array of n integers for Christmas. However, while playing with it over the winter break, he accidentally dropped it in his XOR machine and the array got lost. Okay. So you have an array of n integers, at most 10 to the 9. There's at most 500 of them. The XOR machine is currently configured with a query of size k, which cannot be changed. And you're allowed to perform the following type of query. By giving the machine k distinct indices, you get the XOR. Okay. You help them recover the XOR sum of the array by querying the XOR machine. Let d be the minimum number of queries needed to find the XOR array with query size. Your program is expected to find the XOR sum in at most d queries. And also, it's also possible that it's not possible. I'll put -1 immediately and do not begin interaction. Okay. So they do give a case where it's impossible, so it's probably actually impossible and not just some troll. Is it worth reading F1? Let's take a look to see how fast good people solve F1. Okay, pretty fast, but it's only 3 people right now. I don't know. I think that's up in the air. I think. Yeah. Okay, I'll skim over F1. Difference is constraint on here. F2, it's, what, is it big? Wait a minute. Oh, okay, it's a different problem. Okay, let me think about E for a little bit. So, if the query size is at most 1, it's obvious, always possible, do n queries. When is it not possible? Well, okay, I guess something that's really interesting is that if it's possible to recover the XOR sum, you can do it in almost 500 queries. I think that's really interesting. Like, it's not 500 squared, or like however many pairs there are. I guess we could just do like prefixes. Find it. Okay, let's find an upper bound. Is it? Yeah, upper bound. We can always do it like that. Yeah, so we can find, if we have like 5 or like 6 elements, for example, and our window size is 4. We get this, this, and this. We can always retrieve. I query this and this. We'll get the XOR of these 2 numbers. If we get the XOR of those 2 numbers, yeah, because if we have this range and this range, this is like A, I guess this is B, and this is like X, Y, Z, whatever. We have the XOR of A, X, Y, Z. We also have the XOR of B with X, Y, Z. From this information, we can always get A XOR B. Not only can we always get A XOR B, but I guess, I mean, if we XOR it with this, we'll just get B XOR box. Okay. Do we have to figure out the order of these elements? X is a XOR sum. Oh, wait. We only need to find the XOR sum. Oh, shit. I didn't even realize that. If n mod k is equal to 0, it's... Okay, if n is divisible by k, it is always possible and d is equal to n over k. Yeah. Okay, so 5 and 3 is apparently it is apparently possible. If we have 5 spots, we essentially want to get A's or B, A's or this, and so on. This might be some linear algebra logic. That's possible. 5 and 3. 5 and 3 is apparently always possible. Okay, so no matter what, our first query has to get like some k elements. So for example, we'll know what A's or B's or C is. Think of array as 500 bits. Oh. If each query gives bit string with exactly a bit set, we want to find that's what we're trying to find here. So it's exactly k, yeah. If it's exactly k, then how do we do it? One, two, three, 2, 3, 5, 4, 1, 5. Yeah, because if we combine all of these bit strings together, 1 appears. Wait a minute. Oh, it doesn't necessarily represent an actual strategy. That's fair. Yeah, because we can get what value 4 is, we can get what values 1 and 5 are. At least the XOR of 1 and 5. We can get the XOR of 2 and 3. Well, okay, I mean, it's not necessarily an optimal strategy. Okay, so if it's ABC, and then we do something like, obviously we would need to take some integers in here. Let's assume we take everything in here, so there's some left over in here. So for example, if we have C, XOR D, XOR E, in order to include these values, we would need to pick an A, B, and then an E. The XOR of these will get everything but one number. Oh, wait. If we XOR like ABC, okay, so we have XOR ABC. If we XOR like BCD, and we take these XOR, we'll have A and D, but we don't have B and C, but we can get B, C, E in one query. So this is a valid set of 3 queries. And we have all 5 in 3 queries. Yeah. If n is 3 and k is 2, can we do that? K is 2. A XOR B. But like we can never have extra space like this. I think D is equal to the ceiling of n over k. Might need some proof. Has no room. It's impossible. If last query has no room, then I think it's impossible. Because what that means is that clearly we can like get those first k and then like split it into a smaller problem. This is the same as like doing that. Yeah, because in here, like, this is because we can remove by a length of 2 and a length of 2. And then by parity, it might not work. Do I try this? 47 solves. Is this hard enough for it to have only 47 solves? No, I'll try it. I think it's at least worth a shot. Okay, let's see. This is problem E. We need to read it in N and K. N and K, we have 4, 0, 1. If we query this first number, we get these 3 in place. Yeah. Are these one indexed? Yeah, they are. Yeah. Because, like, we have this block of integers. We have k extra integers. At least k of these will be unaffected. Wait a minute. If there's at least k, because we want to have k extra elements left over. Yeah, because it's basically using 2 queries to get those last elements. Because if it's like 2 and it's odd, we can take something like, they can take this, the missing number, and a number we already know. That way when we XOR it, everything we have so far, we get that. Wait, hold on. If it's like 7, for example, we know this, we know this, we know this. Okay, so if I get x and y, it's like x or y, then this last element will never be possible. Oh yeah, because 3 and 2 is not possible. I think that makes sense. Wait, but is it ever possible to do it with like 4 elements and we have 3 left over? No, because like we can't ever take advantage of these elements anyway. I guess, hold on, if it's k minus 1. Yeah, because if we leave a block out, we might be able to have access to forming a block of k minus 1. Maybe. But no matter what we do, even if we query all k elements in here, I mean, I guess we could do like everything except in here, and I could like increase it by that amount. Yeah. I mean, I feel like for 2, it's not very obvious. But if it's something like, the most k numbers in here, if we use like k minus 1 of them, and then we turn this one off. Okay, so we have x missing spots left over, and let's assume this is strictly greater than k. But while at the same time x is less than 2k. If we were to take k minus 1 items away and then add a k plus 1, yeah, because if we were letting this going missing, like we have like k, this is like k plus 2 or something. We query this when we have 2 elements to expose. Yeah, but in here it's like ABC, we can do BCD. We expose 2 elements, unexpose 1 element. I guess I do want that full window. Yeah. I think having that full window is always a good thing. Oh, okay, this is annoying to implement, I think. Is it though? I don't know. I don't know. Just, is there anything getting hacked right now? Good. Good. No hacks, please. If it's possible. Yeah, clearly this is always possible and is easy if n is always divisible by k. If n is not. Yeah, this. Yeah, because if it's like increase 1, decrease 1, it's mod. Or I guess its residue doesn't change at all. K is guaranteed to be less than or equal to n. Okay. Slide window of length k. Okay, I'm going to do it in a really stupid way. K times n over k. Yeah. K times n over k. That should fill up those blocks. Because the thing about this block is that our parity is 2, but doing this, we essentially, the number of leftover things we do, we decrease it by 1, so parity 2 becomes parity 1, increase by 2, parity 3. Parity of 3 is parity 0, which is perfect. Okay, so integer residue is equal to n mod k. NSM was 500. Yeah, n squared is okay. For right is greater than 0 and tags at right is equal to 0. Have a number like this, Oh, I guess we always just want to have a block like that. Yeah. So it's like this. If our residue is n over k, these are like left points. Yeah. Because if we have a block like this, we want to start here and end there. Yeah. Int removed. I guess it's k minus left. Yeah, we remove k minus left things, and we add left things. Yeah. And temp is going to be equal to. This means we create yeah, so if we initially had residue, where it's like the number of blank spots we have, we add or removed, we subtract add. Residue minus add. Yeah, because like it's itself. Wait a minute, hold on. So we remove that many, so we add on to here. Yeah, because initially we had 2. If we add on 2, subtract 1, it becomes 3. Residue minus add. Residue. So if temp is equal to 0, so if it works, no, well I guess if it doesn't work. Okay, so if n mod k is equal to 0, this is like the easy case. We do this. establish the first block. Because this is our first block. Yeah, because it's a residue check over here. Oh, I never used tags. That's funny. I guess I can just do something like this. Find offset block in residue. Included at I is equal to 1. Minimize number, minimize removed. Yeah, so we want to minimize remove. We can minimize this when can we do this? I guess we just like loop over here. Yeah. Left point is equal to -1. Left point is equal to left. Make offset query. Okay, so int right point is equal to this, like left plus, if left plus k minus 1 is greater than or equal to k, then we break. Yeah, because there's not enough room for everything. Then we do this. Include an I gets sorted by 1. Reds is equal to first. Yeah, because we're just querying this. Get rest. Instead of 4. k. If okay, so if included occur is equal to 0, then should always equal k. Count is less than k. I'm not. What do I do here? I'm gonna do this for now. Okay. This should be okay. Then we just do let's try this, see if it works or not. Like, first off, let's see if 3, 2 gives -1. Okay. Make sure 5 and 3 works. Nope. Okay. Hopefully this is an easy fix. Removed is equal to k. Okay, if left is equal to 1. Removed, add. Wait, hold on. Oh, it's n. It's greater than or equal to n. Now, my bad. I was just being stupid. Okay. Make sure 3, 2 still gives -1, which it doesn't anymore. That's awkward. Okay, let's just query 5 and 3 first. Wait, what? If temp is equal to 0. I got it backwards. Wait a minute, hold on. That's not right. That just doesn't make any sense. 5 and 3. It gave 2 and 1. I guess left, like the left index. Nope, not what I want, not what I want, not what I want. 5 and 3. Yeah, 2 is removed, 1 is added. Residue is equal to k. Or no, residue is equal to 2. Because n mod 3 is equal to 2. So it's 2. Oh wait, this should be subtracted. Okay, I was just being an idiot. Wait, removed increases by this amount. It's not by residue, it should be by k. Yeah, these variables aren't right at all. Because all we care about is like whether it's like it mod k. Mod k, mod k. Well, like this is subtraction. Yeah, something like this. Removed is k minus left, add is left. Okay, that should be a little bit better. question is it better to fix everything? 3, 2 now gives -1. 5, 3 now makes a valid query. Okay, that's nice. The XOR of 1, 2, 3 is equal to 4. Yeah. The XOR of 2, 3, and 4 is 1 XOR 7 XOR 5. 1 XOR 5 XOR 7. 1, 1, 0. It should be 3. 2, 3, 5. So 1, 7, and 6. Shouldn't that just be 0? I think it's just 0. Yeah. Okay, I want to submit. How many people solved it so far? 127. Let me make sure I'm like doing this endpoint correctly. I'm breaking at the right point. This is easy. If temp is equal to 0. Yeah, because I want to include as many as possible. Like, not remove. Like, remove a minimum number. Let's see. I might, if I'm still stuck on F, if I'm stuck on E, I might spend some time to look at F1 soon. Wrong answer, pretest 4. I wonder why. Wrong answer, pretest 3, pretest 4, pretest 4. Interesting. Interesting. Wait, so who solved it? Okay. Am I doing well? Okay, that's pretty good, I guess. Okay, I want to see if this gives runtime error or not. If count is less than k, then this... Oh, wait, I wouldn't know, though. Oh, I'll do TLE then. Yeah, this will TLE if count is less than k. And count should always be equal to k. So I'll just use this to help me debug what's going on. Right? Yeah. I'm gonna walk around a bit. Okay, it still gave wrong answer, so it's not necessarily because it's breaking here. Huh. Let me make sure I'm not being dumb for n mod k case. So if it's like 10 and then 2. Actually no, let's do 12 and 3. 3, 0, 4, 5, 6, 1, 7, 8, 9, 10, 11, 12. Yeah, that's fine. That seems okay. I don't have to worry about this at all. Does this ever exceed 500? No, it doesn't. I wonder if 11 and 2 is possible. No, it's not. Is 11 and 3 possible? It is. I wonder if it's possible for anything as long as it's not 2. I feel no, that can't be right. Okay, if it's 11, 4, let me just verify this. 1, 2, 3, 4. We have a block of 4 already settled. 1, 2, 3. So if we have in here, I guess if 11 and 4 is impossible, then by default that means 7 and 4 is impossible. Yeah, because right now we have A, XOR B, XOR C, XOR D. We could get D, XOR X, XOR Y, XOR Z. Yeah, and that would not do anything. Or we could do C, XOR D, XOR. You know, it's like A, B, C, C, D. It's like we add 2, remove 2 is the same thing. Yeah. Or if it's something like this, we remove 3, we add 1. We remove 3, we add 1. That way we only know A and X. But if we only know this one and this one, then we're solving the same problem on 5 and 4. And that doesn't really help us. Yeah, so that doesn't seem any good. Is 13 and 4 possible? No. 13 and 5, I think, is possible. Yeah. I mean, by by the same logic, we could just say 8 and 5 is possible. Oh, wait, what the hell? Wait, hold on. 13 and 5? 13 and 5 is possible. So why is 8 and 5 not possible? Oh, because it probably like extended on that range. Maybe. Let me see. Okay, so it's like the same thing over here. 8 and it's like mod 3. Let's assume we have A, XOR B, XOR C, XOR D, XOR E. We want to find X, Y, and Z. So obviously we could do, we want to query by 5. So we could either get everything but D and E, at least 2. Or we can get something like C, XOR D, XOR E, XOR X, XOR Y. Yeah, we won't know Z, we won't know these. So it's 4. Wait, but why is 13 and 5 okay then? Because if 13 and 5 Yeah, because like at most one move, this is how many blank spots we can have. Left work equals crew. 8 and 5 is not possible. 13 and 5 is. And I gave the endpoint at 4. Oh, so we remove exactly one value. Yeah, I guess that makes sense. Because in here, we always have to remove at least 2. But if we remove just one value, then it's just like E, X, Y, Z, and like some blank number. Doesn't really matter. But it's just like, we increase by 3. No, wait. We made 4 numbers known while making 1 number unknown. So in one move we made 3 unknown. Yeah. Or like we make 3 known because we make 4 here and then here. We turn it off at that position. 4 and here. Yeah. Okay. Well, that makes enough sense. Let me just make sure that this is okay though. If I just pick let me just pick some smaller values so I can debug this. Maybe like 7 and 3. If it was 7 and 3, what if I fill these out with like 1, 2, 7, 4, 12, 3. Just 12, 3, and 5. I don't know. Just, yeah. Online Zor calculator. Input base 10, input base 10, output base 10. Yes, like for example, 1 and 2 should give 3. Let me just confirm this. Yep. So then if it's like 3 and first 3 numbers like 3 and 7, it should be 4. So this gave 4. 1, 2, 3. And we do 3, 4, 5. 7 Zor 4 Zor 12. Okay. 3 Zor 12 gave 15. So this should be 15. And then this is 1, 2, 3, 3, 4, 5, 6, 7. Okay. And so 7 Zor 3 Zor 5. So we 4 Zor 5, that should just be 1. Yeah. And then we get a Zor total of 10. I wonder if that's right or not. Let's see. One Zor 2 Zor 7 Zor 4 Zor 12 Zor 3 Zor 5. Does it give 10? It does. Huh, okay. So it does seem to be giving the right value. For that test case at least. Maybe it's not super obvious, son. Maybe. Wait, was this 10 to the 9? Did I use longs? Yeah, that's probably fine. made 3 queries on here. Maybe it's possible to make more queries? Like, okay, what if we have a value that's like this? System.out.print. Okay, well, an upper bound is ceiling of this. Doing it like that. If we get the rest of them, then what if instead of 7s or 3 was 4s or 3? Is that even possible? No. Because we have these values. Literally our only possible offset is here. And doing that will leave 2 values instead of 1. Oh wait, hold on. What do we have 2 values instead of 1? If we have like 2 and then like 2 undiscovered over here, then if we set this range and we have 1, 0, 0, 0, 4 and 3 is possible. 4 and 3 is actually possible. Okay. Roughly 4 and 3 should be possible in how many moves? Okay, so this is in 1 move. Wait, hold on. This is in 1 move, we get this. In 2 moves, we get this. In 3 moves, we get this, and then in 4 moves, we can get everything. So it should be 1, 2, 3, 4 in 4 moves. So we might need to do like a BFS type of thing. Yeah. I think we want to do a BFS to find if there's a path from our current parity to a parity of 0, or like a residue of 0. Okay. X1534 E2. I just stop it. No. Let me make a new file. X1534 E2. Okay. I'll save my old copy in case if I need it. But I think if we make updates like this, it could work. Yeah, we just like want to take every move, because we're only looking at like 1 layer in. We want to maybe do more. The maximum number of moves it'll take, obviously if it's equal to 1, is 250. 250 moves that most that. Okay, so 502 shouldn't, it's always possible anyway. It's like 499 and 2, that's not possible. Yeah. Yeah, because like from here to here to here, we want to have like a state of, if we mark it as the number of 1s turned on, or I guess number of 0. Yeah. Distance at new number of moves to get to residue equals 0 from residue equals x. Okay, so clearly this is correct. Otherwise, we want to, I guess I'll remove a bunch of stuff, write it from scratch. Minimum number of moves to get residue 0 from residue of x. New int residue can be, I guess I only care about residues of k. Because distance of 0 is equal to 0. Yeah, residue is equal to like a number of 0 spots. And then for how do we transition? I guess we iterate over how many we can turn off, how many we can turn on, stuff like that. Residue. Does that work? I think it does. Yeah, because if we take those, it doesn't really matter. We need like almost k of them to influence in the first place. Yeah, because it's like making this many number of moves and making this and this and this. Because this is what we want at the end. Or at least something like that. How much time do we have? A little over an hour. I think we can do this in an hour. I don't know I don't know if I should read F right now. Or F1. Maybe later. I'll just quickly look over G and H. Because You know, it's fun. Why are there 800,000 numbers in the input? That's so dumb. And there's 3 interactive problems in this contest? What? Okay. Sure. I mean, I guess that's allowed. What? Oh my god. Okay, so we want to get like from here to here. Huh. Let me think. So if we draw, so we have like a bucket in here. There's always maybe we just do a BFS. I mean, if we want to make it like really simple, then there's total n² transitions. No, n² states. And each n² state has a transition of about that much. So it might work. It honestly might work. Yeah, because we care about, the only thing that really matters is how many of those. I mean, well, okay, we won't even be visiting most of those states anyway. It's literally just how many are currently off and how many are currently, it's just how many currently off and how many currently on. It's just n minus that number. So if we do like, I mean, we could just do a BFS from that. If we did how many was like currently turned on, if that number was like equal to this, yeah, and then we can just like make a set of moves that follows that number. The only thing that we care about is how many units are turned on or are turned off. To force x yeah, distance at n plus 1. Distance at n is our goal. Yeah, and like this parent is equal to this. Yeah, we want to maintain parents so that we know what kind of moves to make. Q dot add at 0 because number makes 0. Or I guess, wait, we're going backwards. Because it's easier to backtrack parents like that. Because if we do this, our next node is equal to this. Or I guess like a parent node of this is equal to that. We just go down that path. Yeah. So we actually want to start from n, and distance at n is equal to 0. So int empty, if empty is less than or equal to k, the number of spots that we turn on as empty is equal to this. We want to first figure out whether it's even possible to do this in the first place or not. So if empty is strictly greater than cur, or I guess n minus cur, how many current spots are occupied? So it's like a number of empty spots. Let me break. Yeah. Otherwise we make this transition. And next being equal to cur minus number of empty spots that we took over. Filled is equal to k minus empty. So we turn the filled spots into here. Why don't we do that? Yeah. If next is less than or equal to n and distance at next is equal to -1, then distance at next is equal to distance at cur plus 1, and then the parent of next is equal to cur. Yeah, and eventually, hopefully, we reach the distance of 0. So, in other words, we do k and then we do n. Okay. So now, 4 and 3 should be possible. Or at least it should recognize it's possible. Line 55, if next is less than or equal to n, if empty is greater than this, I guess we should just do number of empty spots that we want to take over. It's equal to minimum of k and n minus cur. If we do this, then it's like this, cur minus fill plus empty. Let's see if this helps or not. No. Cur plus filled plus empty. 4 and 3. 1, 3, 0. If next is less than, okay, well, next has to be greater than or equal to 0. Okay, that is okay. Let's get some more information about what distance of 0 is. Should be equal to 4 or something like that. 2. Why is it 2? Like if we have 0 filled up, the parent of 0 is equal to 1. How do we make that transition? How is it possible to go from 1 to 0? Oh, I guess it is. Wait, no, this is 0 occupied spots. Wait, no, we want to make it... We transition from 1 Wait a minute, hold on. So if it's like this, cur is how many like full spots we have. Yeah. Because we just want to flip them. How do we get from 1? Cur filled empty. One, two, one. Filled. Oh. We don't want filled to exceed that. Yeah. If filled is great. If number filled that we have to take away strictly greater than that, then we don't want to touch it. 4 and 3. I think that sounds better. Yeah, because like 0 unoccupied spots to 3 unoccupied spots, that makes a lot more sense. Okay. Let's try it. Let's give it a shot. The complexity, there's up to n transitions, there's n states total, that should be fine. That shouldn't be a problem whatsoever. Int tags, int res is equal to 0. We initially start off like this. Int. So while true, and then we just make this journey, or like this path. So int off is equal to 0. Okay, so if off is equal to n, then we break. And then we have our answer. Otherwise, we need to find the answer. Or I guess it's more of that situation. Yeah. Find the next move. Into next is equal to parent at off. Wait, because we go from 4 empty spots to 3. Wait a minute. Are we sure this is right? 0 empty spots becomes 3 empty spots. Or no, so for X spots to be occupied. These are like full spots, so. Okay, in one move we can turn 0 full spots to 3 full spots. That's actually correct. Okay, yeah, that's fine. I just got a little confused. We got a little confused in my brain. I think I'm really close. I'm taking a long time on it, but it's just implementation. So next move is equal to this. If we make a move like here, and then we move it to the next. So like, how would we implement that? we need to check what this next move is. So our next value is equal to like a next residue parity, I guess. So this kind of move, k is equal to 0. Oh yeah. This is like, we'll like first loop over how many values we could do. So if it's off, min, off, and then k. Like if we go from 0, we make a move, that affects 0 of the already occupied spots and adds it onto the rest. So this is equal to off plus k minus a minus a. Okay, so if k minus a is equal to the number of off pieces. Wait, no, this is the number of off pieces that we iterate over. So it's like, if we do that, we make a move from here to here. Yeah, for int. Yeah, so if we have this many turned off, wait, off, this should be on. That's why it seemed a little confusing. I was like, yeah, because we start from 0, right? We start from 0 on. Yeah, it's just n minus 1. So if it's equal to on, if this is equal to how many like on segments that we delete, then it should be something like, okay, well, if n minus 1 is less than or equal to, if n minus 1 is less than or equal to this value, look, yeah, number of off things. Minimum of k and on. Yeah, because we can only change at most that many. Yeah, so on is equal to number of ones in here. A is equal to how many ons that we choose to disable. We want to check to make sure because we need to, if we disable this many, then we would need to take like, I guess, k minus a empty spots. And if this is strictly greater than here, then we move on. Yeah. Otherwise, if it's possible, then we want to find out what this transition is. So it's like on minus Yeah, on is like a number of currently on. We want to turn off A, and we turn on this many. And so if booth is next equal to parent at 1, then choice is equal to -1. Then we know that this is a choice of how many like of these we need to pick. Okay, so if choice is greater than 0, else we want to add on if tag at I, or I guess tags at I, if this is equal to 0, then we do this. If tags at I is equal to 1, okay, so these are the values that we turn on, or off, I guess. Oh, wait, hold on, that's not right. Maybe the choice function, maybe I broke this. Let's see. No, okay, that's correct. Okay, so if tags at I is equal to 1, then we want to add disposition of I. So if choice is equal to 0, then we break out of this loop. Yeah, we want to do this. Yeah. So if LS size is equal to K, then we break. Otherwise, we do this. Okay, XOR of 1, 2, 3 is 4. XOR of 1, 2, 4 is equal to, that's equal to 3. 5 XOR 3. What is that equal to? That's equal to 6. 1, 2, and 5. That's XOR 3. 6 XOR 3. That's equal to 1, 0, 1, which is equal to 5. Okay? I don't know. Okay, let's see if this is any better or not. See how many solves there is. 278. Okay, I think I'll... F1 doesn't... Okay, F1 doesn't seem too hard. Yeah, mine's taking a long time to judge. There's a hack on A. How? How is there a hack on A? What? I can't even... How does that even happen? Also, why is the queue backed up? Like, see, this is... This... They like... I feel like this is why you shouldn't have, like, 3 interactive problems in one contest. Because if that happens, then this queue, because interactive problems take a really long time to judge. So, it's going to take a really long time for these solutions to judge. Yeah, that's... I don't know how they didn't recognize that happening. I'm going to read F for now. The easy version of a problem. The difference between the versions is a constraint on AI. You may make hacks only if both problems are solved. Dude, the queue is so backed up. Oh my goodness. Okay, let me make sure. Okay, I did see a hack on A, so I might end up hacking A if it comes down to it. They share an edge. Yeah, it means it's checkerboard, right? What else would it be? Red or white, such that every red cell only has white neighbors in the red cell, and yada yada. Yeah, right here I'm just like, I just check both possibilities because there's only 2 possibilities in the first place. And then check it with grid to see, okay, if this is not like a blank spot and it's not equal and it conflicts with this, then it's not possible over here. Yeah, I feel like there's nothing wrong with my A. Like, I can't really think about what could be wrong with my A. You know what's wrong with the Q though? The fact that it's still backed up. Dude, did they really not see this coming? 3 interactive problems, 1D and 1E. Both are like problems that a lot of people will submit on. You would think they would realize that the Q would be kind of screwed, but no, apparently they didn't. Oh my god, what the hell? 28, 29? What is this Q? It's like, is it 50 pages long? Okay, at least it's not that long. It's not a 50-page long queue. It's like 40 maybe? Yeah, it's like 40 pages. What? That's so... Oh god, that's gross. What is this queue? I mean, I guess it's technically only like 6 minutes, like 7 minutes right now. But that's still, oh my god, that's still really annoying. I'll just read F while I wait for that to grade. Actually, I'm gonna run some stuff on here to make sure that my thing, because I'm gonna lose a lot of debugging time if this isn't correct. So I'm just gonna test a few things on my computer. 7s or 4 is 3. 3s or 12 is equal to 15. That's 15. 1, 2, 4. 7s or 4 is 12. I think. Wait, no, it's not. It's 3. Yeah, it's 3. Essentially 3s or 3. So it's equal to 0. 3, 4, and 1. 3, 4, and 1. 7s or 12 equals 11. 11s or 3 is equal to 8. 2, 3, 4. 4s or 3 is equal to 7. That I know. 7s or 12. That's equal to 11. Now, is the XOR of all this 12? It is. Okay. Nice. Let me make sure that there isn't a restriction that, like, these indices have to be in increasing order. Okay, they don't. It showed in the input. Yeah. Wow, this queue is really screwed up right now, isn't it? Yeah, this queue. Yeah, I'll look at F1 for now. So you received a puzzle from his friend and you need his help. The puzzle consists of an upright board with n rows and m columns of cells. Some cells are empty and some are filled with blocks of sand and m non-negative integers. In this version of a problem, this will be equal to the number of blocks of sand in column A. In column I. Okay. When a cell is filled with a block of sand, it's disturbed, a block of sand will fall from a cell to the sand counter at the bottom of a column. While a bottom block of sand is falling, other blocks of sand that are adjacent to falling will also be disturbed and start to fall. Specifically, a block of sand disturbed at cell ij will pass through all cells below and including a cell within the column. The cells adjacent to a cell ij are defined as here. Okay. In on operation, you can disturb any piece of sand. The puzzle solved when there are at least this many blocks of sand counted. I don't understand what this is asking. By disturbing both blocks of sand on the first row, on the top, I don't understand what this is saying. Oh, we got E. Yeah, we got it. Let's go. We'll take that. Okay, let's go. We got E. Bog. Let's see. F. I don't understand the statement for F. I just don't. Oh wait, how fast did my E run? Okay, that hopefully won't be an issue. Okay, we got E. Let's look at F. Or F1, I guess. The puzzle consists of an upright board with n rows and m columns of cells. Some are empty, some are filled with blocks of sand. When a cell filled with a block of sand is disturbed, it will fall from its cell to the sand counter at the bottom of a column. I don't think I understand what this is doing. For example 1, by disturbing both blocks of sand on the first and here and the block of sand on the second row from the top, in the fourth column from the left. I don't understand what this is saying. Do I try to hack people? I guess I could try to do that. I'll think about this a little bit more. So we have here other blocks of sand that are adjacent to any point in the following block of sand. Specifically, a block of sand distributed at cell ij. All cells below and including. of an upright board with n rows, m columns. Some are empty and some are filled with cells. Okay. When a cell filled with a block of sand is disturbed, the block of sand will fall from its cell to the sand counter at the bottom. Oh, okay. I think I understand what it's saying. So it's like a spread. Yeah, because it's like disturb that here will pass through all cells below, disturbing all adjacent cells along the way. Yeah, so it's like this cell will disturb this one. This will fall down here. Yeah, because like in this case, we need to disturb everything. In here, by moving this down here, we can disturb this one, which in turn will disturb this one, which in turn, does it disturb this one? I think it does. Yeah, okay. That's interesting. That's kind of interesting. I'm not immediately sure how to do it though. I'll think about it a little bit more. But that seems pretty cool. Seems like a good problem. What happens if we do something like this? Okay, we might want to, I think one way we could think about this is determine which, like think of, okay, this, I don't know if I'd be able to solve this. Okay, how about this? I want to look at standings to see like how important hacks are. Like how much would they benefit me? Honestly, not that much. Are there any other hacks happening? It's just A so far. Yeah, he's like trying to fix it. You have to at least this many blocks. Okay, what's a hard version? A hard version? AI will always be not greater than equal. Oh, wait. That did not occur to me. A will equal the number of stands in the column I. So we just want to find the minimum number to trigger all of them, to trigger all cells. Oh. Okay, well, there aren't that many cells to begin with. So you might want to think about how to trigger a cell that's on top of it. Because if you take a cell, activate all cells. How do we do this? I guess we don't need to read this last line of input then. We just need to make sure we touch all of these cells. Maybe it's like we can draw a graph of some sort. Or maybe it's like, if you look at the first row that has, like the topmost row that has blocks of sand, you want to cover them in here. Take a block of sand up here, drop it on top of it to here. Wait, the cells can trigger going up as well. Yeah, because going down here can make it go up like that. Yeah. That kind of makes sense. Okay, so obviously for a column going down, yeah, okay. So the first rule is that we only want to, in every column, we want to take at most one block. And the block we take has to be the one at the top. So for each column, we must take at most one cell. If we do, it's the top one. Also, if we think about which cell like triggers which, we can like go from the top and then we can just figure out which collection, if we were to disturb that one by itself, what collection of cells would it be disturbed by? What's the time limit? 2 seconds. Oh god, wait, that's a really tight time limit. What about... Okay, that's fine. That's probably fine as well. Oh, he's not doing it. Okay. If we disturb a cell at the top, okay. So we take this, fill it down. Okay, so in here, the leftmost triggered cell is over here. And here, the leftmost triggered cell is here. But we can also do it up, all the way up to here. Okay, so if it's like a connected component, like this, then we can just touch any one of those cells and it'd be okay. Yeah, because like it's not necessarily number of components, because one component can potentially disturb another component. But if we get these components, so like in this case, I guess if we disturb, yeah, disturbing this component, if we like first get the components using flood fill, yeah, so like this is its own component, this is its own component. This disturbs This will eventually disturb this component and this component, which in turn we would want to check to see which of those components it would disturb, and so on. Is there ever a situation in which that happens, where if we trigger this component, the other component will be triggered as well? I'm not sure. I am not sure. I'm going to float around for a little bit. Yeah, so like for each, I guess we could even think about it just like for each cell, right? Like if a cell was triggered, we would draw an edge from here to here. This cell was triggered, we do it from here to here. Or, but like we want to think of it as how it's together. Yeah, I'm gonna try this. We have about 20 minutes. If I speed through this, it's honestly possible. But let me get fast scanner. Okay, so this is our BFS. I want to do it by each row. Oh, no, by each column. So it's preset of m things. Yeah, so we do sets at c. If it's equal to this, then we add r. We add directed edges now. So for int r is equal to 0, r is less than n, and r plus plus. Okay. For int c is equal to we don't want to add too many edges, so yeah, I guess that's big enough. What? Even funnier number. Actually, wait, no. Funnier number. There we go. This is m. We do okay, well, if sets at if c is greater than 0 and sets at c minus 1 dot size is greater than 0 and sets at c minus 1 dot, we want to get the ceiling, or I guess if the last element is greater than or equal to r, int a is equal to tags at r and c. Okay, so greater rc is equal to the dot, then we continue, because we're not interested in that. Int b is equal to sets at c minus 1 dot ceiling at r. A does not equal to b, and sets and edges dot add cons times a plus b. Set edge set edges at a dot add b. If c plus 1 is less than m and sets at c plus 1 dot size is greater than 0 and sets at c plus 1 dot last greater than or equal to r, sets at c plus 1 dot ceiling at r, and then something over here. If sets at c dot size is greater than 0 and sets at c dot last is strictly greater than r, then we want to go down. int b is equal to set c dot. And then same thing over here. Okay. Top sort. Or I guess to not necessarily a top sort, but rather just top sort-ish logic. Okay, so we do less than equal to booths. Or in next. Okay, let's see if this works or not. 3 and oh, I got 2. It's supposed to be 1 though. Wait, it is 1 though. Oh wait. Vowels of 0 is equal to 0. That's why I had 1 extra. But that is also weird because that means that this is supposed to be, it gave 2 when it's supposed to be 3. I have 8 minutes to debug this. I don't know if I'll be able to do that, but I will try my best. Public static void print grid. Okay. If debug print tags. Oh shit! I'm so dumb. Oh, I just realized something. This is supposed to be this is a index itself. Int b should be equal to grid at bb at c minus 1. Int b should be equal to grid at bb c plus 1. And int b should be equal to grid at, well, this is grid at bb c. Yeah, that makes a little bit more sense. Line 35, 114 for int next. Or not grid, tags. Oh, it's still 2. Okay, what if I set this to be? Let me just make sure that the tags themselves aren't screwed up. 1, 2, 0. Oh god, it's not checking all of the states. Oh, what? Really now? It's not checking all the states. Why is that? Oh, M. Okay, I got 3. I got 1. We're gonna have to submit this right now. Oh, the debugger. False. Alright, I submitted. Are you serious? Wrong answer pretest 10? Oh, come on, dude. Oh my god. What? That's not fair. N and M. N and M. N and M. M and N. Okay. Yeah, because we add the row in here. Res is equal to 0. Do we do an actual top sort? No, I'm not sure how that would help us. If C plus 1 is less than M, and this and this. Yeah, because it can go adjacent like that. It's set to that last is strictly in R. Then we go to the ceiling over here. Tags at B, B, and C. Tags should work fine now. Yeah. If grid at RC is equal to 0, no, if it's equal to this. If it's this, and, okay, if it's, we haven't visited before, and it's equal to that. We assign it equal to this, and then we move on. If we haven't seen this node before, and that. Yeah, that's probably fine. Is it a big submission? Kind of. Tree sets. We only add it in here if it's that. Yeah. Okay. We trigger this, but by going down here, yeah, that's why we check this adjacent thing, because it has to be triggered by some intermediary in here. Cons times A at B. What if I just make this bigger for some reason? God, that's so unfortunate, dude. Print. If debug print. Okay, if we do this, Okay, what if I just do like a 2x2 grid that's just that? That's 0. I'm just trying some desperate stuff at this point. Q and Q. Oh, shoot! I thought, dude, I thought I had it, and then it just screwed me over. Come on, man. Come on. You know what the worst thing is? I think I know how to fix this. I think I actually know how to fix this. I just need like a little more time. Okay. Whatever. Alright, that's my contest. I hope you did well. I don't know what else to say. That's kind of sad.